previous method will be overcome how we are going to overcome this method. We are discussing this method. And coming to the application results. So application results means here we are going to test our method. It has 4 numerical examples. We are taking 4 examples here. So those methods, the 4 methods will be done by all the methods that we are having: Luca, Goodman, Lassie method, and our proposed method. So that is from the comparison, you can easily understand what is the improved version of the response. So this we are finding the test response here. So that will be compared with the other methods or the existing method, and what is the improvement of that we will see in the application results and future results and will see. So that is now up to now this method is applicable for the only for the linear time varying system, not for the other method. So that I am trying to guide and myself is trying to improve the invariant, not variant system, and also directly oriented. So that will be the future one. So next coming to this objective. So this is the object of the method, proposed method. That is to develop a method, new method. That is to reduce the higher order system, that is linear time varying system, and reduce the lower order. So while reducing the convergence differentiation technique, at the same time we are retaining the, so we are taking the higher order system to the stable one. So that will be after reduction, that will also retain the stable state, and also we are maintaining the time varying parameters and initial marker parameters also retain same as this. That is the advantage of this method. Next coming to the need. So first one is the need modeling. So modeling here, that is we are modeling the higher order system. So suppose we take the design of the higher order system, so it is very complicated. So because of the order system increases, so the number of components and design system is very complicated. So that we go for the real-time application will be complicated. So that will be reduced to the lower order. And then that will be, so that means after getting the lower order, so whatever the response we are getting in higher order, that will be same or improved version of the reduced order. So that will be modeling here, order reduction of the same. And coming to the stable reduced order model on the state original system. So that means after addition of the system from the higher order system to lower order, so that system will be stable. So we will reduce to lower order. Suppose we take the 8th order or 10th order system, that will be reduced to 2nd order system. It will be easy to implement that. Because the number of components will be very less, so automatically we can easily design or implement the system. So that is the next one. Next one is here the main advantage of this method is here maintaining the transient as well as the second system will be safe. So you compare with the original system, you find what is the transient response, but the steady state will be same as the after addition of the second order, the lower order system, this will be same. That is the main advantage of this one. Next coming to the overcome limitations of the previous or present existing method. That means to take the variant or Lucas or Goodman method, those will be some of the drawbacks. Suppose you take the example which is needed while seeing your application results, you can compare with what is the drawbacks, how we are going to overcome the drawbacks and Lucas by this method. Next one is the differentiation method. So here we take any system that will be described or analyzed by the transfer function model. So that is here the original system transfer function is given by the first equation. So that is in terms of the equation of the transfer function. So in terms of that one, by using the equation of the original transfer function here method, it will be reduced to second order. So after this case this is the reduced model, and first one equation is the original system model. So after reduction of the system from the higher order to lower order, you can get this equation with the coefficient of the small letters you get the after reduction of the system to the lower order, you are getting some coefficient that will be the model. Next coming to the, so here you are describing the method. So originally you are having the original system with the transfer function model, that is called the numerator and denominator. So initially you are reducing the denominator factor to the lower order. So you have got this generalize the equation. That is, we are finding the coefficient first. With the help of the coefficient, we are developing the denominator. Generally, we are reducing the numerator of the original system to the lower half of the original system. So this is of the denominator reduction class. Now we are doing. So that is we are here. We are using the technique which is called the differentiation technique. So this is a generalized reduction process of the denominator factor. So that is DKR between this one. So we are here. We are finding the differential technique. Nothing but we are finding the factorial of this one. So here the factorial will be finding this one. P will be P factorial by Q factorial into P minus Q factorial. This is after finding the application of the several denominator factors. Generalized equation will be even like this our method. So the DK will be sigma equal to K plus 1. So that is the K indicates the GS, the order of the system. You take the original system order will be higher order, that might be 10 order, 100 order. That will be reduced to depending on the system, that the K will be reduced order model, and K will be 1 or 2. Generally, here in this method, we are reducing the second order system. So then only it will be easy to implement. Next, coming to the how we are going to reduce the numerator. So here also, we are finding the retaining the original parameter, that is the time moment, and our initial master parameters. So that is the K. When K equal to G, M indicates the T is the time moment parameter, and M is the initial master parameter. So here we are partitioning this is the entire numerator into two parts. So that is the T1 to P power K and so this one is the first part, and second one is the master parameter. So that is we are participating the entire numerator from higher order system to the lower order with the help of these two participations. That is the first part indicates the moment time on parameter, and second part we are indicating the initial master parameter. So that means we are retaining the time moment and initial master parameter same as the original system, even though a reduction process is there. So that is the advantage of this method. So here the coefficient TD and the MM. So it is the time moment parameter, and initial master parameter will be calculated by this equation. This is after analyzing the equation. Finally, we are generalizing for the any system to get the time moment parameters and the initial master parameters. So then coming to the application results. Here, after reduction of the description method, there is this proposed method. We are apply this method to taking the numerical example. So this is first numerical example, application results. So here, the first one indicates a original system. So which is having the order of the fourth order. So that is the denominator factor indicates the order of the system. So that is the S14 indicates the order of the system. So N equal to here 4, and that will be reduced to second order system. So actually our original system is a fourth order system, that will be reduced to second order system, which is S1 already increased the distance with the previous. How we are going to reduce the denominator polynomial, that is the dt of S. So it will be given to this after getting the S. So here we are finding reduction process means we are finding the factorial of this one. So here NC to indicate the N here, that is the original system order, that is fourth order system, and getting the original dt of S. And finally, by taking the second order system numerator reduction, that is the LTI System getting this one. So this is the after of S indicates this proposed reduction of our proposed method is this one transfer function model, and that one is LTI indicates the original system transfer function model. So after that, the application will be the MATLAB. We have implemented with the MATLAB. That is we are finding set transforms here. So you see here, this is the left set transforms indicates the color. The color is in red, indicates the original set transform. And coming to this, so the green will indicate the set transform which is proposed by our method. So if we the set transform original system and compared with our proposing method, the transient as well as the steady response will be improved. So that means the transient response is died out as it as possible compared to original system. So that is the improvement or advantage of our method. And coming to the second advantage of this one, so by taking the rule of Goodman, here the difference between the order of the numerator, denominator, and the unique consequence should be one only. So if it is more than one, so it is unable to find apply the low-cost method. Whereas coming to our proposed method, we can implement whatever it may be different. It may be 1 or 2 or whatever may be, we can easily get the improved version of the set response here. So that is the main advantage of our method. So in the original system, so other than one. So the entire indicates the original system response and green color indicates our regular model set response. So the transient response is died as early as possible compared to original system. This is a second numerical example. So here also, finally, set response of the three methods, that is the Goodman method. So here the difference only between the numerator coming with transfer function. This is the difference between the regular model, numerator and denominator, and the difference only one method. So you can also apply the Goodman method. So whereas coming to more than one, not possible. So that is the drawback of Goodman. That drawback is also overcome by this our method. So this is our example. Here also, same we find the difference between the original system. Difference between the numerator and denominator, we have only single difference. You can apply all the methods. So that is we are getting the response here also the same as the improved version of this. The green color indicates or the set response of the proposed method. So that is the response will be greatest as early as possible to the steady state, and also the transient will be. So same time, whatever the sum they will take, the Lucas and Goodman and cardiac transmission method. Here, the original system is a stable one. It is stable. After addition of those methods, by the Lucas and Goodman method, that will be failed in phase. So that is system will become unstable some cases. So whereas coming to the by method, our method will be always stable. System will be original system will be stable. So this is our application oriented result. Improved also result. Next, coming to the peak table. So after our method is limited to only linear time invariant system, not for the variant or other method, other variant system. So that we are trying to improve the linear variant system also, and also we are trying to apply the bidimensional variant. So if it is a systematic system, described by the differential equation, we can easily analyze by this method, and also you have to find out the response. It is on higher order system to the lower order. So non-linear system also will apply in the time. And coming to the conclusion. So in our method, so the main advantage of this method is, even though after addition higher order to lower order, we are retaining the time moment and the initial markup parameters to the original system. So whatever the time moment and the initial markup parameters will be there, that will be retained in the reduced order model also. So that is the system conclusion. Thank you.